All right, this is Mr. Wyrick, and I'm here to go over the Unit 4 test review with you as well as I possibly can. A reflection across the x-axis. This is going to be a small r, and in the subscript, it's going to be x-axis. And what's going to happen here is my x, comma y is going to become, when we're reflecting across an x-axis, we keep the x the same way. The y becomes the opposite. On the next one, a reflection across the y-axis. This is an r, and then we have y-axis in the subscript. This is going to go from being x, comma y to being a negative x, comma y. If we reflect across either one of the axes, the x-axis or the y-axis, we keep that same value. So the x-axis, we keep the x. The y-axis, we keep the y. A reflection across the line y equals x is r, and then in the subscript y equals x. Keep in mind, this is lowercase r. The rotation will be a capital. This is going to go from being x, comma y to being y, comma x. We're going to see those values swap when we reflect across that line. And then a reflection across the line y equals negative x. Again, an r with the subscript of y equals negative x. And this is going to go from being x, comma y to being negative y, negative x. Okay? Not only are they going to switch, but the sign in front is going to change as well. The formula in both notations for the translations. Translations are a capital T, and then we're on this one, 6 units left, we're going to have a subscript of negative 6, comma 0. No change to the y value, or x minus 6, y. Moving 4 units up, that's a translation with a subscript of 0 and then 4. And this is going to be x and then y plus 4. Moving 3 units to the right and 6 units down is going to be translation 3, negative 6. So that's x plus 3 and y minus 6. And then moving 2 units to the left and 1 unit up, that's a t with a subscript of negative 2 and 1. And that's going to be x minus 2 and y plus 1. So basically what's going on, if we're moving to the right, we add to the x. If we are moving to the left, we subtract from the x. If we are moving up, we add to the y. If we're moving down, we subtract from y. Okay, on the second page, we've got our rotations, and rotations are that capital R. So a rotation about the origin, 90 degrees. Counterclockwise is kind of the standard. So that's really what we're looking for there, is that counterclockwise rotation. What this is going to do is change our x, comma y into a negative y, comma x. We swap those values, and the one that's in front now is going to become negative. A rotation of 180 degrees counterclockwise, R0 of 180 degrees, a rotation about the origin of 180 degrees. And on this one, clockwise, counterclockwise, doesn't really matter. You end up in the same spot. This one's going to go x, comma y is going to become a negative x, negative y. It's awfully close to some of those reflections. So you really have to make sure you're differentiating on this one. The rotation 270 degrees is a rotation about the origin of 270. This should be x, comma y is going to become y, negative x. Okay, we'll swap them, and that x value becomes negative. 90 degrees clockwise about the origin is a negative 90 degrees. Almost forgot my degrees symbol there. And that negative 90 degrees is going to be the same as 270 degrees. So my x, comma y is going to be the same thing as the one right before it. Now, if there's any other clockwise rotations on your test, they match up. Clockwise 180 would be the same as clockwise, counterclockwise 180, and clockwise 270 is the same as 90 counterclockwise. So if you can follow along with those, you can even make a note out here to the side if you really want. The dilations, you draw a square. It's at 2, 2, 2, 4, 4, 2, 4, 4. So we can see this is a square. All the sides are 2 units. And when we dilate the square by a scale factor of 1/2, we are multiplying every single value there by half. So 1/2 of 2 is 1. 1/2 of 2, 4 would be 1, 2. 4, 2 would be 2, 1. And then 4, 4 is going to look like this. I got that in the wrong spot, didn't I? I did. So sorry, this original square should have actually been here at 2, 2. They overlap. So you can ignore this one up here. Oopsies, oopsies. Everyone will be fine with it. Dilate the square once by a factor of 2. So if we're going a scale factor of 2, 2, 2 multiplied by 2 becomes 4, 4, which is this point that we already had. And then the others become yeah, here we go. 8, 4. One, 2, 3, 4. Yeah, I feel like I'm just off this morning on getting this on the graph properly. But this is a 4x4 square that you can see there. Okay, so it kind of moves away from the side. This is the original right here, number 1. This is number 2, dilating by 1/2, and then this up here is number 3, dilating by a factor of 2. The last bit that we're covering here is the symmetry. The lines of reflectional symmetry, this one with the logo only has 1. A circle would have a whole lot, but this, because of the logo, it's only going to have 1. Every time we bisect a side of a regular polygon, or every time we bisect an angle of a regular polygon, we are going to end up with lines of symmetry. So for this regular octagon, we end up with 8 lines of symmetry. Now this last one is just a crazy logo. This is, I think, the Empire from Star Wars. So each one of these little tines that's sticking out would be an axis of symmetry, and we connect one to the other. So there's 3, but also halfway in between them would also work as a line of symmetry. So we're going to end up with 6. The order of rotational symmetry is, remember how far we can turn it around. If we look at this Volkswagen logo and we actually do try to turn it, because of the logo, the only time it's going to be congruent to itself is when we turn 360 degrees. So it also has an order of 1. The regular octagon here, we can turn this on each of the flat sides, which means that's going to go 8 times. And this one, if we turn it to where the new tines are up at the top, well, we've got our original, and it goes 1, 2, 3, 4, 5, and then 6. So it just so happened that our lines of reflectional symmetry matched up to our rotational symmetry. That won't always be the case. If we have something like a rhombus or a parallelogram, this would have 0 lines of reflectional symmetry. There's nowhere that we could draw a line down through it and actually get that parallelogram to reflect, but it would have an order of 2 in rotational symmetry. Hopefully this will get you through this review. Hopefully it'll get you through the test, and good luck.